Hey, my name is Johnny Pavlak. I am doing my presentation 1 for ME360 Fluid Engineering, and this is going to be it. Alright, so for this problem, we have been given the streamline function for a flow that is actually going to be coming down into a source. So the source is going to be right here at the origin. We have our X and our Y coordinates. The flow, I have a red pen for that. So the flow is going to actually come down. It's going to stop right here because our source is pushing up from here, while our flow is going to get kind of pushed off to the side by that source. And what it does is it actually creates a little bump that looks something like that. I know it's not good looking, but it looks like that. Knowing this, where these two meet, it's going to create a stagnation point right there. That stagnation point, or the height of the bump, is given to us as well as a term H. The strength of this source is given to us as a term M, and we're actually given the streamline function for this flow coming down into our bump, and it is psi is equal to AXY. In class, we actually derived the streamline function for a source, so that's psi is equal to, let's say for a source, is equal to in class it was Q, but in this case the power of the source is M, so M over 2 pi theta. So with these two sources, one's obviously in cylindrical and this one's given X and Y, we can go ahead and switch the AX and Y into cylindrical real quick. So in cylindrical, we know X is equal to R cosine theta, Y is equal to R sine theta. We'll write it out as A is, these two are just going to replace these two. So we'll get a R squared cosine theta sine theta. It's really close to the double angle formula, and we can actually manipulate it a little bit by saying multiplying by 2 and dividing by 2. That gives us our double angle, actually, by saying a r squared over 2 is sine 2 theta. So now that we have our two sources, using superposition, we just want one streamline function. So a streamline is going to be equal to streamline 1 plus streamline 2. We'll say this is 1 and the source is 2. So really our streamline for the whole problem is going to be AR squared over 2 sine 2 theta plus M over 2 pi theta. Now, we actually in class also derived quite a few functions for relating our stream function psi to our velocity. And in this problem, since we're trying to relate our constant A, our M, which is our power, and our H, we need to make use of those velocities. So we know that the velocity with respect to R was defined as 1 over R d psi with respect to theta. So if we plug in our psi that we're given, we can find that velocity. And if we use those velocities, we know a stagnation point obviously means there's no fluid movement for that time being. So we can say that the velocity is 0 at these points. So really quick, we'll figure out our VR. So keep all that. Oops, that's a second derivative d, not a regular d. Plug in our terms, AR squared over 2 sine 2 theta. You can do both together. I like to separate them since they're separated from a plus. Just makes it look a little bit cleaner in my opinion. All right, so we have a theta in both terms. The r squared over 2 are constants in this case, so we can put those out. Same on this side, the m and the 2 pi, or m over 2 pi. So that's going to give us a with respect to r, 1 over r. So like I said, ar squared over 2 are constants, and then the derivative of sine 2 theta just gives us 2 cosine 2 theta. In this case, sorry, that's not supposed to be there yet. M over 2 pi, the theta cancels out, and that just leaves m over 2 pi. We can clean it up a little bit by throwing this r in there, and then also we have a 2 over 2, so those are going to cancel each other out. Velocity with respect to r is going to be equal to, for this one, one of the r's is going to cancel out, ar cosine 2 theta plus, and there's nothing to cancel out in this term, so we're just going to add that r to the bottom, 2 pi r. So now we know our velocity with respect to r. We can find our velocity with respect to theta as well, considering that's also a function of psi. We define that as velocity with respect to r is equal to negative d psi over dr. So kind of do the same thing with a little bit less steps, because we don't have the 1 over r, so we know that you're going to keep that negative. Going to plug in that psi that we found up top. So ar squared over 2 sine 2 theta. Once again, I like to separate them out. Makes it a little bit cleaner. M 2 pi theta. It's really good in this case too, because the second term doesn't have an r, so the whole term is going to go ahead and cancel out. The a over 2 and the sine 2 theta are going to be constants, so we can bring those out. Gives us e theta is equal to a negative, and then all we're doing is of r squared, so that's not too bad. Just gives us a r sine of 2 theta. So we have our 2. Like I said, at this stagnation point, we're going to have a 0. So this VR and this V theta are going to equal 0 at that point. And then if we find the coordinates given to us on this graph, we can also plug those in, and that'll help us form the relation from H, A, and M. So our theta is just starting at the positive x-axis, going to our stagnation point. Luckily, it's on that 90-degree angle, so we know theta is going to be pi over 2. And then our r is just the height out, which we're given as h. So we know that theta is pi over 2, and r is h. So kind of keep that in our heads. And we actually go ahead and just use one of them to solve. We'll say, remember VR is equal to a r cosine 2 theta plus m over 2 pi r. Taking these two, we sub them in, and like I said, at that stagnation point, r is 0. So 0 is equal to a r. We're going to sub in the h. Cosine 2 theta, we sub in pi over 2 plus m over 2 pi r, we sub in h again. This actually cancels out, so it just gives us cosine of pi, which we know is -1. So 0 is negative 8h plus m over 2 pi h. So we're trying to find a and m, the relationship with h, so let's go ahead and isolate h. We'll start by moving that one over, 2 pi h. Let's go ahead and multiply by h, gives us h squared, m over 2 pi, divide by a, h squared is m over 2 pi a, and then just one simple square root gives us h is the square root of m over 2 pi a. And that is all we were looking for in this case is a way to relate the height of that bump, H, to our constant A and the power that the source had, M. And that's our problem. Oh, let me sign it.